really well today for some unknown reason. It's an unhappy machine day. Hold on.
We are recording and we do have audio and video.
I know. Well, at least, oh, there we go. This is a non-traditional beginning to our video today. Sorry. The machine was not happy today. This is an unhappy machine day. Okay, here we go. Sorry. The machine wasn't happy. I spent like the last 10 minutes trying to get it started. Well, we have a good attendance today. And I know why. Because you're all very excited about the lecture today. You're like, oh my God, I can't wait to get there and find out about the stationary distribution of ergodic Markov chains. I know I felt the same way when I was your age too. But the wait is now over. And here we go. This is a really cool lecture, actually, as these sorts of things go. So I'm going to switch over to the document camera and get started. Okay, so we're doing section 9.4 today. It's very cool. So the basic idea is this, and I think I mentioned this a little bit before, that, okay, so you have a Markov chain. Okay, and a Markov chain, and it's going to be like x0, then x1, x2, okay? So these are states. And each new state is only dependent upon the previous one and then some probability distribution, right? So basically, this is I and this is J, say, okay? And then T, so let me say it's IJ. It's the probability then that x3 equals J given x2 equals I, which, if it's a homogeneous Markov chain, is the probability that xn is equal to J given that xn minus 1 is equal to I. Okay? So that's kind of how it works. This thing here is the transition probability from one state to the next. And if you're an electrical engineer, you probably feel like, if you do this long enough, let me also say that then, what happens is that if you write this as a matrix, then you have pi, say, of 0, right, times p. So this is going to be like a vector times a matrix. So if you have one element of this vector, it would sort of pick off a single row. So the row has to sum to 1, and each row represents the probability distribution of all the transitions possible from a particular state. So that thing is going to be equal to then the new thing, which is going to be pi 1 in this case. Okay? So this is a matrix P with elements Pij. Now, then if you have, so you continue this and you say, well, pi n is going to be equal to pi 0 times p to the n, right? So basically, this is like kind of a geometric series of these transitions. They just keep multiplying together as matrices. And, electrical engineers naturally think that if you have something like this that's repeating, eventually it's going to reach steady state. Now that may not actually be true, but if you're an electrical engineer, you think that's true, because in electrical engineering, that's how things are. You drive something with a system, and eventually there's a transient, and then the system reaches steady state. So if you believe that, then you'd say, well, sort of pi of infinity is going to be equal to pi 0 times pn as n goes to infinity. Right? Well, pi 0 isn't a function of n, so that would be like pi 0 is equal to the limit as n goes to infinity of p of n. So, if you believe that this Markov chain would reach steady state, and you believe that if you raise p to some power n, and n is large enough, eventually it converges to something that should be p of infinity, right? And if that's the case, then you would expect that p of infinity, all the rows of p of infinity are equal, because no matter what initial state you start in, you get to the same steady state distribution, presumably. That would seem like a logical thing to assume. In fact, it's not really true, but it is sometimes true. If this happens, then this Markov chain, first of all, the Markov chain needs to be stationary, right? Because if the p's are changing with time, then, you know, it's not so hopeful that the thing's going to reach a steady state. But if the thing is homogeneous, so the p transition probabilities are invariant in time, then you would expect if you apply it long enough, eventually it should reach some kind of steady state, right? Now, one would expect that, except for it's not true, unfortunately. Well, or fortunately, because if it were true, then there would be all kinds of weird things about the universe that would be messed up. So, yeah. So this is kind of how it works. Okay, there's basically three things that can go wrong when you. There's three reasons why you might not reach steady state. This is, and this is like in a difference equation. You know, when you look for the homogeneous solution of a difference equation, it's like this is like the homogeneous solution. There's three reasons why it might not converge with steady state. And the three reasons are actually stated right here. The density may become trapped in the next, this is on page 198. The density may become trapped in disconnected state. The density can become periodic, or the density can disperse. Okay? So, okay. The first thing is trapped. Okay, so let's say you have, so now I'm going to draw like the state. There's a different, the way I just drew the states here, it's like this is a graph in time. Each node of the graph represents the next time, right? But there's another way that people draw graphs to illustrate Markov chains, and that's with sort of a state transition graph. So, so for instance, let's say you have, yeah, this is an easy one. Okay, let's say you have two states. So n here is equal to 2. So xn is got to be equal to entry 0 or 1. Okay. And now the probability, let's see, so you have say x, so this is state 0, this is state 1. And what happens is that if you start in state 1, you go back to state 1 with probability 1, okay? And if you start in state 0, you go back to state 0, probability 1, right? So the transition matrix for this, Pij, so this is the input state and that's the output. So if you start in state 0, then you'll always go back to state 0 with probability 1. So this is going to be a 1 and that's going to be 0. If you start in state 1, then you go back to state 1 with probability 1, because that's the transition matrix, right? It's the identity. And then P equals I, so P to the n also equals I. So whatever state you started, you just end it. So this doesn't reach an ergodic solution, because if you start in state 0, you stay in state 0 forever. And if you start in state 1, you stay in state 1 forever. So therefore, it doesn't reach a steady state solution which is independent of the initial state. I guess there's a steady state solution, but it's not independent of the initial state. So in this case, so our hope is that, so P of infinity here is equal to I. The hope would be that P of infinity has like rows, and each row is the same. This is the pi infinity, and the last row is pi infinity. So each row of P is, that would be the hope. But in this case, it's not true. Okay, so this is one case. You can become trapped, okay? So in this case, we say that the Markov chain is reducible because you can basically reduce it into two different Markov chains which have, which are not connected, right? And the next possibility is that it can become periodic. Okay, so this is an easy one to do. We have 0 and 1. So in this case, if you start at state 0, you go to state 1 with probability 1. If you start at state 1, you go to probability 0 with probability 1. So now in this case, P of ij is a matrix, and it's 0, 1, 1, 0. So then P to the n is equal to 0, 1, 1, 0 if n is odd, and it's equal to 1, 0, 0, 1 if n is even. So you never reach a steady state distribution in this case. In the odd, at the odd times, you're in a state 1, and in the even times, you're state 0, if you start in state 0. If you start in state 1, then it's the opposite. So, this is like a clock. The states are periodic. Okay? So that's the second counterexample. Okay? The third counterexample is when the density is dispersed. So let's say you have this is dispersed. So let's say n here is equal to infinity, so that x of n is a member of the set 0 through ... I won't put infinity because it doesn't include infinity. So it's 1, ... 1, 2, 3. It's counting numbers, right? Oh, no, hold on. I'm sorry. And we want to be able to mix it down. So it's 0, minus 1, minus 2, ... And this is 1, 2, ... like that. Okay? So it's all the counting numbers. Now what you do is you say, okay, so B sub n, these are independent and identically distributed with the B sub n equals 1. The probability that B sub n equals 1 is equal to the probability that B sub n is equal to minus 1. And then say equals the probability that b sub n equals 0 is equal to 1/3. So, in every time you have a 1/3, b sub n can be either 1, minus 1, or 0 with probability 1/3. And then we make it so that x sub n is equal to x sub n minus 1 plus b sub n. This is a random walk. I'll put this piece of paper in here so I can write more easily. This is a random walk. And what will happen then is that, you say, well, so what does it look like? Random walk, well, you start up, let's say that well, let's say you started off at 0. And what will happen is, it's like this. Like, you can't really draw a random walk, because human beings are incredibly bad at producing random sequences that are truly, uniform. If you ask somebody to generate a sequence of 1 to 0, this is a great experiment. Ask somebody to generate a random sequence of 1 to 0. If you analyze the sequence, there'll be all kinds of really strong correlations. Because human beings are really bad at that. Typically, I think what people will do, I'm not an expert on this, but if you ask them to generate a long sequence of random 1s and 0s, you'll find that it'll be too correlated, right? Anti-correlated. They'll make it, when you just have real random sequences, people think to see correlations. It's like looking up at the clouds and seeing a dog, right? Or a chicken or something, or listening to an administrator and thinking you heard something intelligent. It's like something you fabricate in your mind based upon random inputs. So, so what happens is that, so you have this random walk. Now, what happens what happens is that the expected value of xn equals 0 for all n, right? Because the expected value of bn is 0, right? And so if the expected value of, well, actually, I really should write it more generally like this. The expected value of xn given x0 is equal to x0 for all n. That's the more accurate thing. I'm assuming you started off at state 0. So whatever initial state you're in, the expected value of all future states is equal to the initial value. So this is called a martingale, right? So I don't know why they call it a martingale, but they do, okay? And there's also a thing called a sub-martingale and a super-martingale. So a sub-martingale, I'm going to get this mixed up. My memory's kind of bad, so don't quote me on this. Go look it up in Wikipedia. But I think a sub-martingale goes up, okay? So the xn, x0 is always a lower bound for the future, and the super-martingale goes down. So the x0 is always a... So if you're gambling is a super-martingale. You always lose money on average, okay? The value, the expected winnings at some point in the future is always less than or equal to the current amount of money that you have, right? And, there's a lot of really interesting results about this. And if you want to study it, it's really quite fascinating. Then you can get into things called stopping time zones, right? So I have to go off on a slight tangent because I can't help myself. I'm sorry. But for those of you who find gambling interesting, I actually find gambling totally uninteresting. From the point of view, if I'm in a casino, I have zero, that piece of my brain must have been removed at childhood because I have no desire whatsoever to gamble. But I find the concept of gambling very interesting. I think it might be because I deeply believe in probability at such a fundamental level that I'm convinced beyond any shadow of a doubt that on average I'm going to lose money, so it doesn't really I don't find it very stimulating, because I in general tend to not dislike losing money. But anyways, the concept of gambling is really quite interesting. And, you know, because what you can do is you can set a threshold, right? And then you could say, well, what I'm going to do is I'm going to gamble until I hit that threshold. So I'll start with some amount of money on this. I might go like this, and then you say, oh, and then when I hit that, I'll stop. Okay, and then I made money, right? So the algorithm is guaranteed to make money because when you stop, you've made money, right? So you'd say, well, that doesn't work because I tried it. I lost all my money. Okay, but you can actually prove that if it's a martingale, if the expected winnings are neutral, okay, that if you wait long enough, the probability, so this is x t, this is a threshold t, and xt, okay, is going to be, so x of t, I'll put here t, okay, it's the time at which it reaches t, okay, well, I don't know, so, okay, I'll do it like this, x, I'll make this a tau, okay, right, it's the time at which it reaches that threshold, okay. So it turns out this thing here, tau, is equal to the minimum, or actually the infimum, over all t, such that the maximum over, say, f greater than t of x of f is greater than the threshold t. This is actually not the minimum, it's called the infimum. Infimum is the technical term for the minimum. So then tau here is a function of the random variable, or the random variables xf. This thing is called the stopping time. And it's a random variable. And intuitively, yeah, that's true. Yeah, that's correct. Intuitively, stopping time is an implementable thing, right? It doesn't require a non-causal knowledge of the future. I mean, in other words, I can always make money in the stock market if I know the future. Okay? But if I only base this on the past, we can show that the stopping time is only a function of the past. Okay? It's essentially it's a random variable which can be formed from the sigma field of all the past information. And you can show the following thing. You can show that the probability that tau, because tau is a random variable, is less than infinity is equal to 1. So with probability 1, if you wait long enough, eventually you'll win. So this is sort of like the double down strategy. What you do is you say, okay, I'll bet was $1. Okay, I flip a coin. If I lose, I say, okay, I'll double my bet. If I win, I keep the winning. And I keep doing that until I win. When I win, I'll win $1. So I can just keep doing that. Sooner or later, I'll win, right? Because I'm flipping a coin. It has to eventually come up heads, okay? So if I'm flipping a coin, right? If I come up heads, I win. If I come up tails, I lose. Every time I bet $1, okay? And I flip it again. I bet $2. I flip it again. I bet $4. I flip it again. I bet $8, right? Well, sooner or later, with probability 1, I'm going to win. And when I do, I'll win $1. You can work it out. So what's the problem with this? I mean, it works, right? You make money with absolute certainty. So you guys should all, I knew you were really pumped about learning about ergodic Markov chains. You should just leave right now, go to Wall Street, and go to it and make some money. Okay? By the way, this was the strategy that a lot of people in Wall Street were using in 2007, okay? Because they never took this course. They never took a course on martingales, okay? Well, it's just that you can prove a theorem, okay? And the theorem is this, that if the stopping time has the property, right, that, well, okay, for this particular stopping time, it turns out that, so what's the catch? You run out of money. So what ends up happening is that the expected value of the absolute value of x, okay, so the expected value of, so we'll do it like this, we'll say the maximum of the absolute value of xt over t less than tau, the expected value of that is infinite. So you need, the problem with this strategy is that you need an infinite bank, okay? What you've really done is you've created a distribution where the probability of winning a small amount of money is very high. So with probability, and so, okay, so then what happens is that once you actually make the bank finite, then so you say, okay, well, I'm going to use that strategy, but I only have $100 million in the bank, okay? So what will happen is that with this strategy, with probability 10 to the, with probability 1 minus 10 to the 10 to the minus 8, okay, you will win $1, okay, right? But with probability 10 to the minus 8, you will lose $1 million, or 100 million, 10 to the 8 dollars, $100 million. So every once in a while, you'll lose an enormous amount of money, but most of the time you'll just make a little bit. So then the trick here to make this profitable is what you have to do is you have to make sure that whenever you win the dollar, you go home really quick and don't answer anybody's questions. And whenever you lose the dollar, you immediately run to the President of the United States and ask for the money back, okay? And say, well, I'm very sorry, it was an accident. Okay? Now, okay, those are called stopping times. You should study them sometime. And there's a lot of interesting theories about martingales and stopping times. And it's actually one of the cases where if you've taken like real analysis and Lebesgue integration and done all the theoretical stuff, it's one of those cases where having the theoretical formulation actually is more or less required in order to get formal proofs of this stuff. So, yes. Anyway, what really so the bottom line is this: as the probability that xn equals any particular state I is going to be decreasing as n gets larger, because the distribution, so it starts off really peaked around 0, right? And then it kind of starts distributing, and then it gets, okay, like this, okay, like that. And the probability that it sort of dissipates out like a cloud, right? And then what happens, so this thing limit as n goes to infinity of this is equal to what? 0, because the probability of any particular state goes to 0 as you wait longer and longer. So the probability dissipates as the random walk, it's like a cloud, like smoke, that just sort of dissipates, spreads out further and further until, you know, if you wait long enough, eventually there's very little of it. So this goes to 0. So there's 3 things that can go wrong. The Markov chain can become trapped in a disconnected state, the density can become periodic, or the densities can disperse. So, and I give three examples. I give three examples here of the three things that can go wrong, but they're basically the same as what I just explained. Now we want to be able to talk about the stationary distribution of Markov chains. Actually, maybe it's not entirely clear, but why? We're going to want to talk about this because it's going to be very useful for some other things we want to do. So we have to, how do we guard against this happening? Well, we're going to have to make some assumptions about the Markov chain. Okay? So I'm going to need some definitions. So we're going to have a concept of communicating states. So two states I and J of a discrete time, discrete state homogeneous Markov chain are said to communicate if there exist integers n and m such that you can get from state I to J with n steps. So when I say you can, I mean the probability is greater than 0. It's possible. It doesn't mean it's likely. It's possible. And that you can get from state J to I in n steps. So if it's possible to get from one state to the other in a finite number of steps, then you say the two states communicate. Okay? Now, if I don't know if we have, so if I communicates with J and J communicates with K, then it's easy to show that I must communicate with K. So it's a transitive property. So it turns out that if you have a transitive property, then it's easy to show that any property with this structure will partition states. Into distinct sets, right? So in other words, you can take all your states. It's just like the region growing algorithm that we did in 637 for anybody who took 637. So if you have some states, so this is a state, and that's a state, and that's a state. So this communicates with this, that communicates with this. So you just keep growing out until you find all the states that communicate. All right? And then there might not be any states left over. If there's no states left over, then it's called irreducible. But if there are states left over, then you can reduce the Markov chain into different sets of states, and these two sets of states don't communicate. Because if they did, if this communicated with that, then everything in this set would have to communicate with everything in that set. So it partitions the states into distinct subsets, okay?
But do the states in the right communicate with each other?
I'm just assuming that these communicate with each other.
And the right can communicate?
And these communicate with each other. So you can partition any finite number, any set of states, even if it's not finite, into any countable number of states. You can partition into a countable set of subsets, okay? Each of which communicate with each other, okay? So that's one thing. Okay, now the next thing is that, so this is just, I'm just saying, this is the definition of irreducible. A discrete time, discrete homogeneous Markov chain is irreducible if for all I and J communicate. So if all the states communicate, it's said to be irreducible. So an irreducible Markov chain eliminates this problem of it being trapped. Okay. This would be reducible. This is not irreducible because these two states do not communicate. Right? Okay. Now there's also a concept of a periodic state. The definition of periodic state is complicated, and so you really have to read it carefully. I'm going to try to go through it here, but it's really kind of good to go on through it very carefully on your own. Okay, so we denote the periodic state I by the value di, where di is the largest integer such that p NII equals 0 whenever n is not divisible by DI. Okay, well that's a sentence, okay? So let's try to think about that. What does that mean? Okay, so okay, first of all, D is going to be the period of the state. So if D is the period of the state, it means that if the state I is periodic with period D, it means that it will return back to that state every D times. And if it's not a multiple of D, then it can't be in the state. So the periodic state is really defined by what doesn't happen, not what does. Okay? It's defined by the fact that if you're not on a clock tick, you can't be in that state. So it's like a clock with with the gears, right? They're discrete and it only repeats every cycle. And if you're not on that cycle, you can't be in that state. Okay? And the reason is, if you could be in that state off cycle, then it would be like the gears had flipped, and now you could return off that cycle, so you could return any of those times, right? So you really define it by where you can't be, not where you can. Okay? So okay. Now in general, okay. Now if D is greater than 1, then we say the state is periodic. So let's say if D equals 1, then it just means you can't return to that state. Oh no. Okay, so everything is divisible by 1. Okay? So everything has periodicity 1, because everything is divisible by 1. So there is no n that's not divisible by 1. So the condition always holds for any state if D equals 1. Right? Now, if D is larger than 1, then it actually means something. It means that when it's not divisible by D, then you can't be in that state. It's a little bit of a confusing definition, but if you stare at it long enough, it makes sense. So this is the concept of a periodic state, okay? And now the problem in the example I gave you was that this state was periodic, and obviously it's periods too, because if you start at state 0, then in time 1 you can't be in state 0. In time 2 you can be in state 0. In time 3 you can't be in state 0. Okay, so anything not divisible by 2, you can't be in state 0. Okay. So periodic states can cause you a problem, but if you exclude periodic states, then you're good to go. Okay. So then, so there's only one other thing to worry about, and that's the idea of dispersing. Well, okay, you can only disperse. The whole concept of this dispersion, the dispersal of the probability, is that you have an infinite number of states. So if you have an infinite number of states, there's an infinite amount of space to spread the peanut butter, right? So you have peanut butter, you put it, if you have a really big piece of bread, then the peanut butter gets really thin, okay? And it gets thinner and thinner, okay? So if you have, but if you only have a finite amount of number of states, well, there's no place for the peanut butter to hide, right? There's only a finite number of states for it to hide in. You can find the peanut butter. So if you put those three things together, you get this very, very, very important result. Now, I should tell you that you can take an entire course on this material, and routinely people do. And we actually taught one in this department, except for almost never gets offered, which is not my fault. You can complain to the department for that. So it's 643, which used to do some of this stuff. But I'm sure they have an advanced stochastic processes course in probability that you could take it too. But I'm like teaching you everything you ever wanted to know about stochastic, about ergodic Markov chain in one lecture, okay? So obviously, I'm giving you the very, very abbreviated version, okay? First of all, I'm not even proving the results. And the other thing is that it turns out that these results hold in all kinds of complicated situations, except for, I can mostly tell you this, anything you think should be true usually is, okay? In fact, I've never actually thought of something that I thought should be true that wasn't. So that's pretty much the overall writing theorem, but I'll give you a particular theorem here. So the particular theorem is this. Now, if the number of states is a finite set, so the finite set means you can't spread the peanut butter to infinity, okay? Now, the Markov chain is irreducible. That means that it doesn't depend what state you started in, because all the states are connected together. Wherever you start, it's like the old thing where you go ask for directions, you go up to the farm and you say, I'm going to Los Angeles, and they go, well, you can't get there from here, okay? Okay, well, you can get anywhere from anywhere, okay? So you can't get stuck, okay? And the Markov chain is aperiodic. It can't be a clock. So if those three things hold, then if you wait long enough, eventually the Markov chain has to converge to a stationary distribution. So what does that mean? That means that there exists a unique stationary distribution pi for which all state I, for all states I is given by this, okay? So you start off in state I, and the limit as you take n goes to infinity, this matrix here, for any state I will converge to the same distribution. So independent of I, this distribution in J converges to the same thing. It doesn't matter which state you start in. If you wait long enough, eventually the distribution will converge to the same steady state distribution independent of the initial state. It doesn't depend on the initial state because all the states are connected. So if you wait long enough, eventually it all gets mixed together, okay? So, and the solution to this can be found by solving, it's going to be the unique solution to the following set of equations. Well, first of all, the pi's have to sum to 1. Okay, if you don't restrict the pi's to be summed to 1, then there'd be trivial solutions. Like you could take the pi's to be 0. If the pi's are all 0, okay, then this equation, okay, then this thing here, equation 9.26, is called the full balance equation. FBE, the full balance equation. And what it says is that this equation says that if you start in the steady state distribution, or the ergodic distribution, and you apply the transition rule, you end up back in the steady state distribution. So if you find a solution to this system of equations, subject to the constraint that the pi's have to sum to 1. Now, if the pi's are 0, you got a problem. Then this will be solved. But if you solve this equation for any other value of the pi's, then you can just renormalize them so they sum to 1. So the summing to 1 is not a big deal. Okay, and these are called the full balance equations. And the solution is, in this case, we say that the Markov chain is ergodic. Okay? Okay, now, you have to be a little careful about the word ergodic. It has kind of different meanings in different contexts. They're related, but not exactly the same. So, if you think that a Markov chain is ergodic, it means, if a homogeneous Markov chain is ergodic, it means that if you wait long enough, it'll reach a steady state distribution that's unique in solution to the full balance equation, okay? In addition, there's a concept of ergodicity for a random process, which is that time averages converge to expectations, right? Now, that's true for an ergodic Markov chain, but you have to wait infinitely long for it to occur, okay? Because you can have a transient behavior initially, right? So it's a little bit different. An ergodic Markov chain is, by definition, a Markov chain with the property that has a steady state solution that solves the full balance equation, and that's unique. And now there are other ways you can ensure these kinds of results. Like you can find a solution. You might not assume that the omegas are finite, but you'd have to assume that, then you have to make other assumptions. Or, the other thing that can happen is if the Markov chain is reducible, then it turns out that there's a set of solutions to the full balance equation. One, a distinct solution depending upon which of the reducible sets you start in. So if you start in one of the reducible sets, you'll always stay there, and you'll reach that steady state distribution. If you start in another one, you'll stay there and reach that one. Okay? So, it's pretty much common sense sort of thing. But this is the big sledgehammer we'll need for the future section, because we're actually going to use this later. What we're going to use this for is that we'll use Markov chains as a way of generating samples from general distributions. Okay? So, how do you generate a random variable that's Gaussian? Well, or exponential. In the beginning, in chapter 2, we found that you pass it through the inverse of the cumulative distribution function, and that will produce a random variable with the desired distribution. Okay? Now, but you can't always do that. If you have, let's say you have a Markov random field. One thing we haven't talked about is how do you generate a sample from a Gaussian Markov random field? Nobody ever asked me how to do that. You might want to generate a sample from that distribution. How would you do it? Well, we're going to show that you can use Markov chains to do it. What you do is you generate a Markov chain of random fields. And it turns out if something has a Gibbs distribution, you can generate a Markov chain which is ergodic and converges to the Gibbs distribution. We'll talk about that later. It's actually quite clever. And that's the basis of a lot of Monte Carlo simulation techniques. There's a so-called Metropolis algorithm, which is the basis of that, and that's very important. But, let's see. Yeah, so the next section is properties of Markov chains. Maybe I'll just go through this fast because we'll get started on this a little bit. We have just a little bit of time. So this is pretty straightforward stuff. I'm not even going to spend a lot of time on it. Maybe you just want to read it yourself. It turns out that if you have a Markov chain and you condition on any path point, let me see. Conditioning on, yeah, okay. If you have a Markov chain, then the conditional distribution of a pixel given all the paths is only dependent upon the previous path, right? Also, if you subsample a Markov chain, it always produces a Markov chain. So if you take this Markov chain, right, and you just took this value, and you took that value, and then over here you have another one, you took that value, that'd be x4, right? So let me zoom out. If you subsample the Markov chain, and actually, it doesn't have to be a uniform subsampling, any subsampling, then clearly this thing only depends on that one. This is just more random stuff that goes on in between. So the subsampling of any Markov chain is a Markov chain. You can prove that. Right? Now what's also true, and this is really cool, and I'll probably have to spend a little bit of time on this next time, is that if you reverse a Markov chain in time, the time reversal of a Markov chain is a Markov chain. That is not obvious. Okay? But it's related to the following fact, which is also not obvious, that if you have two random variables, x and y, so let's say y is conditionally dependent upon x, and then you can multiply by the probability of x, and that's the probability of y and x. Well, now you know the following thing is true, but it's going to startle you once I say it, even though you know it already. Okay? Which is this: that I could just flip this whole thing, and I could just pretend x is dependent upon y. I could just use Bayes' rule and say, well, this is the probability of x given y times the probability of y, and to calculate the probability of x given y, all I do is I take the probability of y given x times the probability of x, right? And I divide it by the probability of y. So Bayes' rule allows you to flip. This is what Bayes' rule is. It allows you to flip causality between any pair of random variables. So you always thought that when you threw the rock broke the window. But it could be that the window threw the rock. Use that on your mother the next time you try to do that, and it won't get you very far, really, but it's worth a try. Okay, so causality is totally unclear in the world of probability. I know in the physical world it is. So think about that. You can use that to reverse Markov chains.
Recording is stopped.
Okay, good.